we'll talk about that. Okay, so here are the directions, and I'm going to show you a sample, by the way, as well. Let me expand my screen a little bit. Okay, so basically what you do, you'll notice that the top part of the directions say your final project should include part A. Essentially, part B is an extension of part A, and this is why I put such heavy emphasis on part A a few weeks ago. Even though part A itself is only worth 4.5% of your grade, part A is 4.5% of your grade. What's interesting is that part A, part B comprises, this is the portion that you did for part A, that is 60%. So my point is that part A, while there's a feature in the grade book that says it's 4.5% of your grade, this is part A also corresponds to 60% of part B. And what that means is because part B is worth 10.5%, that's 60% of 10.5%. My point is that when you combine the two together, part A alone comprises 10% of your total grade. So part A looks small in your grade book, but it ends up being really big in the course of the grand scheme of the course. That's because part A is 4.5% of your grade and also 60% of part B. So if you knock out part A, you're really setting yourself up for success in the class. This is why I put such heavy emphasis on the part A. It seems like, for a few of you all, it seems like I'm really pestering you, and I am. I'm trying to, I know what's coming down the pike, and I want to make sure that you're with me, and that really I wanted to set you up for success and make it easier on you in this class. Anyway, so that's why I was sort of being sort of insistent, persistent, and just a pest with part A. Is just because it leads you up to this week. So the new thing with part B, really all you do is you take your part A and you just do two new things. You conduct a hypothesis test, and you answer the questions for the conclusion section. So what I want to talk about now is these parts. So we're going to do the hypothesis test, show hypothesis test, and discuss any conclusions they might suggest. And then you want to go ahead and discuss your results. So what I'm going to do first is I'm going to do the hypothesis test, show you what that looks like, and then we're going to translate to the Word document. So let me go to my Excel spreadsheet. Hold on just a second. Okay, so you may remember from my other video that this is the part A to my spreadsheet. This is where I had my data, then my data on the jackpot for the Powerball. I did my frequency distribution, and I had my graph, had my stem and leaf plot, and I did my calculations for the descriptive statistics. Okay, so what I want to do now is I want to take all this, I want to take this information, and I want to translate it over into a hypothesis test. So what I'll need is I'm going to copy my data here, and I'm probably going to copy this as well. Oops, I'm going to copy that as well. Copy my descriptive statistics. So I'm going to go over to a new page. Okay, and here it is. So what I have is I have my data right here, just copied and paste, and I brought over my descriptive statistics. Specifically, you'll notice I brought over the mean and the standard deviation. I don't much care about the median or the mode when it comes to the hypothesis test because it doesn't matter. All you need is, remember from last week, whenever you do the calculations, you utilize the mean and the standard deviation. That's why I just brought those two forward. Okay, so your hypothesis test always starts off with a claim. And this kind of goes back to unit one, to the part A of the project. Whenever you asked yourself the question, what do you hope and what do you expect to learn? Well, I'm focusing here on the lottery, and I want to know when's the best time to buy a ticket. Because if you ever, even if you casually watch the lottery, you'll notice that sometimes people win very quickly. The jackpots are won very quickly. Sometimes they build up to really large amounts, but most of the time you don't see the really small prizes, and you don't see the really large prizes. There seems to be a collection here of winnings when it gets to about the 200, 300, 400 million now. you know, maybe you should always play because it's worth so much. The potential's there. It's just $1 or $2. But the point is if you wanted to, if you, we talked about it in Unit 3, I think, in that discussion where we said, would you play? If you're sort of averse to playing, but you want to have a chance at winning, when is the optimal time to really play the lottery? You don't want to play that often, but you want to play every now and then. So what's the best time to play? When do you think you're actually going to win? Now, the chances of winning are still very low, no matter what the prize amount is. But if you notice, the prizes tend to collect at around 200, 300, 400 million. That's when that really starts the jackpots really start to hit. So that's what I'm at. That's the claim is I think the best time to play is when the jackpot is higher than 200 million. That's my claim. I can make this value here, this 200 million, I could make it anything. It could be 300 million, it could be 201 million. It doesn't matter. You pick. It's your guess. It's your hypothesis. The key part of this whole thing, so we've made our claim, now you have to, now you conduct the test. And remember, the very first step is you have to create your hypotheses. Now, go back to your claim. I use the phrase is higher than. And so remember back from Unit 4, our Zoom session there, is that we talked about you got to translate this into hypotheses, and you have a null and an alternative hypotheses. And because it's higher than, it's expressing an inequality. We're not allowing it to be equal to 200,000. So because of that, that means we're saying that the mean jackpot is going to be higher than 200. In other words, this higher than corresponded to the alternative hypothesis. That was the translation. And therefore the null hypothesis, was the opposite. So we flipped it and made it equal. So it's less than or equal to. Now, I could have just as easily written this claim. I could have just as easily written this claim as using higher than or equal to. I could have just as easily done that, and that would make it a null hypothesis. So it's really all how you frame or phrase your claim as to whether you're going to have a null or alternative hypothesis. So you make the claim, and then you translate that into a hypothesis. So that's the first step. The second step is you pick your level of significance. My recommendation, pick 0.05, pick 0.1, pick 0.11, whatever you want. 0.05 is the most common one, so go use it. But it's just a pick. There's no math to it. You just say, I want this one. Go ahead and just pick 0.05 if you want. So you need to identify whether you're dealing with a left tail test, right tail test, two tail test, whatever it is. And this all stems from the alternative hypothesis. It all stems from the alternative hypothesis. And because this is a greater than symbol right here, that means I have a one tail test, and it happens to be a right tail test because it's greater than. Remember how we differentiate that? Which way is the inequality pointing? The inequality is pointing that way. The inequality is pointing to the right. That's how I know. So what does this mean for us? Why do we focus so heavily on what tail? Is because it helps us to identify, just going back to Unit 4, is remember we have the mean in the middle. We have the mean in the middle. And we're trying to find some critical value right here, TC or ZC. So we'll do T, by the way. So we're trying to find some critical value because it's a right tail test. That means that the area to the right is going to be my rejection region. The area to the right of that critical value is going to be my rejection region. So what does that mean? Just to sort of refresh yourself, is that if you get when we do our standardized statistic, if we get a standardized statistic that is right here, that's in the rejection region, so we reject the claim. Oops. Whereas if we get something over here, it doesn't matter where we are, then that would be fail to reject. So this is okay if we're over here. This is reject if we're on the right side. That's the whole point. Now the key is what is this critical value? What is the value? What's the dividing line between fail to reject and reject. There's a line. That's why we call it the critical value. And so remember, that's the fourth step, is you have to take your level of significance and the type of test and whatnot, and determine what that critical value is. This also comes from, if you recall from Unit 4, we have to know our sample size. We have to know whether we know the, remember there's two dividing lines. Do you know your population standard deviation, or can you assume that it is normally distributed? In this case, I want to clear it because I have to go over here. In this case, my sample size is what? How many data points do I have? So I have, looks like I have 30 data values. So because my sample size is 30, so my sample size is 30, n equals 30. Can I assume that it is normally distributed? Is it 30 or 31? I think it's 31 actually. Because my sample size is greater than 30, if you recall from last week, yes, I can pretty much feel confident that it's going to be normally distributed. Hold on a second, I have a phone call real quick. Okay, sorry about that. I had a quick phone call that I had to take care of. So anyways, the point is that remember from Unit 4, the whole point is that if you have to know your sample size, because the sample size helps to drive what table are you going to use to find your critical value. Are you going to use the Z table for the normal distribution, or are you going to use the T table? That's the whole point. You have to know what table you're going to use. So this is why we kept sort of back in part A, we sort of said, hey, get 30 because it helps to make it easier to go use the normal distribution table. But if you have if your sample size is less than 30, by the way, if your sample size is less than 30, which most students' projects are in this class, you have to use the T table, have to. And remember, to use the T table, you need to find whether you have a one-tail or two-tail test, you use your alpha value, and you use your sample size to figure out what that critical value is going to be. I've reviewed that back in Unit 4. That's the same thing out of the homework. Okay, so in my situation, I have a sample size that is greater than 30, which means that I can use the normal distribution table. So I go to the normal distribution table and I find that my Z critical value is 1.645. 1.645. Okay. So I found my critical value. So basically, what does that mean? Go back to the normal distribution table. I'm sorry, the normal distribution. Remember, Z equals 0 is here at the center. That corresponds with the mean of the population. We have a value of 1.645. That's the critical value. That's the critical value. Right here. Meaning what? If I get a Z value that is greater than 1.645, I'm over here somewhere. That means I'm in the rejection region. So now comes then finding the standardized statistic. This is what when I keep saying, if I get a Z value on this side, that means I reject. What's the Z value I'm working towards? The standardized statistic, the standardized test statistic. If this value ends up being greater than 1.645, I would reject. So you have to break out your formula. Now this is the same formula whether you use the T table or the Z table. This is what we discussed back in Unit 4 Zoom session. So you take, you take your sample mean, you subtract off the guess, the hypothesized mean, divided by the standard deviation, divided by the square root of the sample size. Plug in your values. You'll notice that the 268.37 corresponds to the mean, the sample mean. Okay, the 200 here, the 200 corresponds to the value in my guess, my claim, the hypothesized mean. And then we have the standard deviation and then divided by the sample size. And so we do the calculation. You'll see that I plugged that straight into Microsoft Excel and can use it as my calculator. And I get the value Z is equal to Z critical equals 1 point. So let's do that. Make it right. There we go. Z critical equals 1.81. And so what does that mean? Where is that on this number line right here? Well, it's over here, 1.81. It's higher than 1.645. And so it's over here in the rejection region. So because it's higher, so let me do this right here. So because I'm right here now, I have to make my decision. Do I reject or do I fail to reject? I reject because the standardized test statistic of 1.81 is higher than, to the right of, what our critical value of 1.645. So that means I reject the claim. What does that mean though when you reject the claim? And the claim being what? Remember the whole point of this exercise? My claim is that the best time to buy a lottery ticket is when the jackpot is higher than 200 million. Does that mean that you should never buy a ticket? No. It just means that we're talking about the best time, the most frequent time, the most of the winners. It just means that most of the winners, the data says, the data doesn't support the claim. We don't have enough data, or maybe the data doesn't support it at all, that the best time or the most jackpots are higher than 200 million. Okay, so that's the whole thing. Okay, so that's the hypothesis test. What you want to do is you want to copy it. I recommend just go ahead and copy it straight from the book. Go to your Word document for your project. And here's mine. So I'm going to go right to the end. I'm going to go right to the end. And I'm going to, I'm going to probably put it after mine. So I'm going to say hypothesis test. Let me make a little heading for it. And then I'm going to copy and paste. Watch this. Boom. There it is. That's all you have to do, is just do your test in your spreadsheet if you want, or you can do it straight on the Word document too. But I just went ahead and did it on the Excel spreadsheet and copied it, pasted it over here. So now what you do is, let's go back to our assignment. Let's copy the questions. Let's go back to our Word document. Let's copy. Now let's answer some questions. So discuss the weaknesses of your study. The weaknesses is sort of a misnomer here. Keep in mind, we're talking about statistical weaknesses. We're talking about weaknesses, things that affected your data that maybe you didn't account for. What are the factors that may have affected your data? Well, for me, if you go back to my data, take a look at my data. You know, there were some flaws in there. Take a look at this. My most recent winning was in September of 2020. You know, that's way past our date. So I'm not capturing even recent data. That's a problem. So I want to recognize that and say that's a weakness. You know, that may not be true for your data, but that's certainly true for my data here. So that's the whole point, is you want to identify what are some potential things about your data, about the way you got your data, that may have affected your results. So my data is limited in time, namely the data is old or not recent, not the most recent data, okay? Another thing to consider is the type of sampling. I used convenience sampling. Did you use a random sample? Did you use a convenience sample? Because remember, going back to Unit 1, if you use a convenience sample, that sort of destroys the credibility of your test. That heavily weighs upon your results. You may have the right result, but it can't be reliable. Doesn't mean your results are wrong, it's just not reliable. So I use convenience sampling, which means that my results are unreliable, even if accurate. That's the whole point. So you want to talk about other things. What are some other factors um, to account for here, specific to the lottery? And you want to go specific to your project, specific to your. These are sort of generic, but go specific to your actual data. And something from the lottery that's sort of interesting and what affects when prizes are won is um, the size of the jackpot determines or affects how many people play the lottery. In essence, or in essence, the higher the jackpot, the more tickets that are sold. And so the more likelihood that a jackpot will be won. That then causes the size of the jackpot, of the winning jackpot, to be smaller. So in other words, one of the reasons why you don't see super high jackpots, why it's very rare that you see $1 billion jackpot, it's only happened a handful of times, is because the higher the jackpot gets, the more people will say, hey, I'll throw $1 down for a chance to win. That's what happens. And so you don't get prizes that are super, super high because as it gets higher, more people play, more combinations are picked, and the more likelihood that someone's actually going to win. Hold on just one second. Okay, sorry, someone was at my door. Okay, so that's a weakness of the. I'm not accounting for the weakness here. So the weakness is that I am not accounting for the number of tickets that are sold at each prize amount. So in other words, a jackpot that is $20 million will have less number of tickets, whereas a jackpot that has 200, that's valued at 200 million will have more tickets that are sold. I'm not accounting for that in my data. I'm just looking at the jackpot size and asking myself, when is the best time to play? So that's my point is when we talk about weaknesses of your study, you want to look at what are the factors that may have influenced your data that you're not specifically measuring or accounting for when you collect your data. It doesn't mean that there's anything wrong with your project, anything wrong with your data. It's just what are factors there that you maybe haven't accounted for. That's a weakness, and you would want to go discuss that. So, to what population would you feel like extrapolating this? This is specific. You want to have a good handle on who you're studying. So, say for example, I'm talking about Powerball data here. Can I extend my results or extrapolate my results to anything else? Maybe I could extend it to the Mega Millions lottery because the two lotteries are sort of similar. They have similar rules for playing and similar jackpot sizes. That could be an extension. I could take my data and say, well, if the most likely, suppose I was right, I didn't reject my hypothesis. The most likely time to play is when the jackpot reaches 200 million for the Powerball. Well, I'm looking at the Mega Millions, and maybe that's the same thing too. On the other hand, could I extend that to maybe the easy five or the smaller games? No, because the smaller games do not get to $200 million ever. It's rare in those smaller games that you get something more than $1 million. So you want to look for analogs. So if you're, say for example, you're in, you're looking at the average salary of nurses. Could you extend your results to another field? Could you extend that to in another way? Maybe you're looking at the average salary of nurses in the Northeast. Could you take your results and extend that to the Southeast or to the Southwest? I don't know. But that's the point is you want to be clear on what your population presently is that you're studying. And then you want to identify what is another population you could take your results to. And you want to have a why. You want to make sure that you explain why you're making that extension, that extrapolation. Give suggestions for further work in the area. This is sort of an extension on the weaknesses. Basically, what could you do to improve it? For example, I would look at for the work in this area, I would look at in my results here, I would say I would want to know how many tickets are sold. I would want to know other factors maybe is how many tickets do people buy? I buy just one ticket at a time because while I like to play, I don't want to throw away money. But there are people who will buy a dozen tickets, multiple tickets. Um, and there's also, for those of you who play the lottery, there's also this question every time I go to a gas station, I buy one. The question is do you want them on the same ticket? That's always caught me off curious because the belief is that when you buy tickets on lottery tickets on the same ticket, that's less random. There's something weird, that hinky going on. So I would also want to look at and say, well, maybe if do the people who win the lottery, are they buying them on separate tickets or are they putting them on the same ticket? That's sort of a curious thing. So the point is what are the factors that kind of goes back to this? What are the factors affecting your results? And maybe just talk about that too. It says, well, if I did this again, I would want to incorporate this sort of data as well. Okay, so that's sort of what I was thinking here. I said my answer here instead of having to type it out. Explain what leads you to the conclusions you have drawn. This is really sort of a reflection on your data. For example, I failed to reject here. I'm sorry, I rejected. And so what are the conclusions that I've drawn? Basically, that I don't have enough, what the jackpot sizes never really get to a point above 200 million. Most of the jackpot sizes are probably less than 200 million. And so because of that, I'm not, the thing that could be affecting that is the number of tickets, the number of people that play, or the number of tickets that are sold, things of that nature. So that it's just sort of rehashing the explanation, if you will. And what changes would you make to this project? Again, that's sort of another way of saying, identifying your weaknesses, how would you account for those, and how would you fix those if you did it again? That's the whole point. So, okay, so that's the part B to the project. Do your hypothesis test. You got to have, that's why you really have to make sure that your mean and your standard deviation are correct from part A, which is why I put heavy emphasis on that. Do your hypothesis test, copy or place it at the end of your part A, take the conclusion questions and just answer those. And that's it. I hope that you find that the project is not too terrible. The only calculation that you have to do is this, the standardized statistic. This is the only calculation in the entire thing to help you find your critical value. I'm sorry, that should not be critical value. It's standardized test statistic. This is the critical value. That's it. Everything else is just sort of going through the motion. Okay, let me know if you have any questions on part B, and I'll be happy to help out. Okay, and I look forward to kind of catching up with everyone during the course of the week. Hope you have a great day.